Okay, welcome back everyone. I'm hearing a bit of echo here. Someone else got their laptop microphones or loudspeaker on. Right, still hearing that. Is that just the loudspeakers?
Yeah, you're not particularly loud when you're going up.
Okay, all right, we'll get started now. I hope everyone enjoyed their morning tea. I recently attended the 2024 online meeting of the Global Meteor Network, also abbreviated to GMN. Started for me at the wonderful time of 5 a.m. So imagine how tired I was. But anyway, during one of these talks, observing minor planet occultations was mentioned as a possible future use of this network. I've been scratching my head trying to think of a talk for TTSO 18, and suddenly this fell into my lap where I could combine two of my interests. So what is the Global Meteor Network? The goal of this project is to observe meteors with a global network of cameras pointed at the night sky, purchased and installed by citizen scientists. Each camera is connected to a Raspberry Pi running open source software for video capture, compression, and automatic meteor detection. If the same meteor is seen by at least two cameras, then its position and trajectory during the visible portion of its flight can be triangulated. This in turn can allow the meteor's orbit to be back calculated, and for meteorites, in other words, meteors that survive to reach the ground, the location of the debris field can be predicted. A major motivation for the New Zealand regional coordinator of the system was to find the 10th New Zealand meteorite. In newsflash, as of last week, we found it. The system detected a meteorite falling down, predicted the location to be within the Mackenzie Basin near the Mount John University Observatory. I think it was two Thursdays ago, search team went out, and just as they were reaching the sort of optimum point to start searching, someone looked down and found this rock sitting in a depression about this size, and lo and behold, they'd found the meteorite. Now, if you're interested in finding the details on that, just see if you can find any local New Zealand newspapers around that time, or I might even be able to find a few email links if you're interested. I can bring that to you later. Anyway, there's a bit more to the system than just a camera and housing. Both power to the camera and a video stream back to the computer is achieved by a power over Ethernet cable. A short network cable then runs between the power over Ethernet injector and the computer, which is a Raspberry Pi 4 running Linux. The Raspberry Pi runs an open source program that records the video images onto an SD card throughout the night, processes the data in the morning, and then sends the analyzed data out using your Wi-Fi to your home router and finally to the GNM web server. This system is very affordable compared to most astronomy setups, costing me just New Zealand $550 when I purchased it last year. It's nearly a set and forget system, but if, like me, you'll probably become addicted to viewing the results files every morning on the web server to see what your camera's been doing. You'll find time. Addictions find time. A photograph on the left shows my camera mounted on the side of my house, a few feet under the eaves. The blue power over Ethernet cable runs out the back of the housing and through the house wall to ultimately connect to the Raspberry Pi. Photo on the right shows the close-up front view of a typical camera. The most commonly used lens in these systems is a 4mm focal length. f/0.95 lens, giving an approximately 88 by 45 degrees field of view, roughly a quarter of the sky. The lens, camera, and associated electronics are all inside the camera housing, which is a fixed housing. In other words, this is not a tracking camera. Experience has shown the need to apply a silicon sealant around the window and also the screw holes in the front of the camera. Early adapters found water got in and fried your electronics. The image here has been made by stacking all of the video frames taken over the entire night by my camera, and then taking the median value of each pixel in that stack. This has the effect of removing the stars from the image, and is the nearest this system can get to producing a flat field image. In fact, this is what they use for flat fields. Now, the dark regions at the top left and top right of the frame is due to the shield on top of the camera housing that protrudes out in the front. I'm actually toying with the idea of cutting that off, see if it makes a difference. Lower down to the left and right are two of my neighbours' trees. Note, if they were my trees, they would have been cut off to the stump by now. Yeah, sorry, I want to keep them friendly with my neighbours, so good people. And finally, the bright spot along the bottom edge, the right-hand side of the image, is a street lamp. I can't quite get rid of that. Yeah. This image here shows the astrometry report that's produced automatically every day. And it's based on the best frame of the night, as judged by the maximum number of stars detected in the frames. The red diamonds show the predicted positions of the stars from a catalogue, with the size of the diamond indicating the star's magnitude. The yellow circles show the stars detected by the software that could be matched to a position in the star catalogue. The length of the yellow line you see protruding from some of the yellow circles is a measure of the difference between the star's detected position and the catalogue position. You'll notice some of the lines look quite long, but it's not the actual real difference. It's magnified by a factor of 100 to make it visible. The green boxes indicate detected stars that couldn't be matched to the catalogue. This usually happens because the star is too bright to be in that particular catalogue. And finally, you can see some faint white lines, grid lines of right ascension and declination have been overlaid on the image. I think if you look carefully, you'll be able to deduce where my camera is pointing to the southwest, with the South Pole and Cygni Octantis up in the top left corner of the image. Now here we have a very difficult to see, I'm afraid, map of New Zealand and Australia. It looked a lot better when I adjusted the contrast when I was preparing this slide. But anyway, you'll see overlaid on that a series of blue dots. Each dot represents the location of one video camera. New Zealand has 131 active cameras as of when I prepared this talk last month, and Australia only has 30. Sorry, we're ahead of you for once. I'm not sure why some of the dots are smaller or fainter than the others, but I suspect it means the camera hasn't been fully set up yet. I also haven't shown the Chatham Islands, which is way off to the east of New Zealand, but 2 cameras were recently installed there. So it's sort of going around the entire globe. We haven't got to Antarctica yet, but soon. Now, this is another version of the map where I've shown the tracks of the meteors that were detected over the last month, shown as these white lines. I included that because it makes it a little bit easier to see where the cameras are. The tracks, as the camera's view extends about 100 kilometres along the top of its field of view. These tracks don't show the exact locations of the cameras, but serve as a good proxy. And it also makes it a bit clearer where the cameras are in Australia, because those blue dots in the previous slide were very hard to see. At least 2 cameras must observe a meteor in order to be able to triangulate the trajectory, So a single isolated camera is not much use. This is very similar to the occultation situation, where the real value comes when you have two or more observers seeing the same event. Now, here I've listed some other possible uses of the system that could be made from the data from these cameras, which may or may not be implemented in the future. Because you remember, this is an open source system which has been driven by the enthusiasm of volunteers in the system. Now, the first possible use is Meteor persistent trains. I'm not quite sure where they get that term from, but the definition is these are long-lasting luminous phenomena which occasionally linger after a passage of a meteor with durations of up to an hour. Now, the left-hand side is a very dramatic trail left by a meteor over Russia during the day. The right-hand photo is more like what we would expect to see from a GMN camera at night. Now, the photograph here shows a fireball over Croatia and Slovenia, which was recorded by a vehicle's camera on the 28th of Feb 2020 at 10:30 a.m. local time, in other words, during the day. Now, eyewitness counts of daytime fireballs are fairly common, but they're of a little value in working out a trajectory. Photographs or video recordings do allow the trajectory and possibly the location of the debris field to be calculated, but it's very labor intensive compared to using results from our system. They also depend on the images just being available to the researcher. It's quite difficult to track them down. At the moment, the GMN cameras aren't run during the day, as they're being configured for nighttime observations, and so are completely saturated during the day. There appear to be two approaches that can be taken to allow daytime measurements. The first is to automatically reconfigure the camera for daylight each morning and then restoring it to the nighttime configuration on sunset. The other option would be to add a filter slide that will be put in place during the day, having something like a neutral density filter or even the original infrared blocking filter that came with the camera. The disadvantage of the reconfiguration approach is we found that the camera is often unstable for a couple of hours after you change its setup. On the other hand, the filter approach requires a hardware modification to each. I'm sorry, my notes have disappeared off the bottom here. Hardware modification to each camera, together with the enormous additional expense of, when I looked up on the internet, all of $5 to buy one of these filter modules to fit into the camera. But the disadvantage is you require everyone on the network to go and buy one of these and fit it in. So I don't know how much take-up we'll have with that. Now, another use is the software already does absolute photometry of stars visible in the image, albeit in a fairly rough and ready manner. This is because, from the Meteor researchers' point of view, the stars are only there to allow the trajectory of the meteor to be calculated against some coordinate system, in this case, right ascension, declination, equatorial system, and also to allow the meteor's brightness to be measured. Now, I suspect if the photometric reduction procedures were better photometric reduction procedures were used, then the accuracy of the results would be improved, and this is something I've been looking into. I'll probably report back next year on it. My gut feeling is we need to get the uncertainties down to about 0.1 magnitude. As you can see in the graph above, it's typically 0.2. So get down to about 0.1 before we can start to get useful photometry out of these. Now, at the moment, aircraft are a nuisance in the system, especially as they resemble meteors in the images and require some very sophisticated processing to be able to identify as being an aircraft and not a meteor. Nevertheless, measuring the presence or absence of a contrail could be used to assist climate researchers in validating their models that predict contrails. So why do you want to do that? Well, I found from listening to this talk that approximately 50% of the climate change due to aviation is from contrails. Now, a member of the network has already developed his own code to track aircraft and overlay the position and flight data on each image, using the addition of a very cheap radio receiver that picks up the flight data broadcasts from all civilian aircraft around the world. This operates twice a day at both day and night observations. This code also allows contrail recognition and can associate the contrail with any particular flight. Now, the idea behind this is if you can improve the prediction models so that you get real-time, reliable predictions of where in the atmosphere a contrail would form at any one moment, the flights can easily be rerouted slightly, just 1,000 feet higher or lower, to avoid that area and avoid the creation of a contrail. And that far outweighs the slight extra expense in fuel being used to achieve that flight change. So that's something we'll keep an eye on for the future. Now, another use is outreach, not only for school kids, but for the public in general. Now, thanks to several grants from the New Zealand Ministry of Education, a large number of these systems have been installed in New Zealand schools. Now, while New Zealand hasn't run a STEM type of program yet with the system, it has been done in several other countries. So I think it's only a matter of time before one of our teachers picks up and runs with the system. Now, on to what you're really interested in, occultations using this. Now, the expected pipeline, at least at a very high level, is pretty similar to the one we do when we're observing and measuring an occultation. However, as most members of this network are not familiar with occultations, I want to automate as much of this process as I can. So first thing we need is predictions of pending occultations. So my first thought on this is during the day, while the camera's finished processing the previous night's data, it goes to Occult Watcher Cloud and scrapes from it the predictions for the pending night that could occur near this particular camera. Now, the existing software already knows where the camera is pointing, so it knows its location and it knows the types of stars, the area it can see, its field of view, and it already has a masking image to cut out the view from the trees and rooftops and so on that otherwise obstruct your view. So you can very quickly work out whether you're going to see a particular star that's due to be occulted or not. However, I do need to look into this quite a lot further, and I'll probably end up having to set up a GMN community tag in Occult Watcher Cloud to just pick out the bright stars, because those are the only stars we can see with this camera system. My camera goes down to about 7th magnitude. And in the meantime, while I was first looking at this, I just did a global prediction using Occult over this entire year for all stars brighter than magnitude 7 and got 244 results. Considering there are 1,226 active cameras around the world at the moment, I think this number means it's worth pursuing this idea that we'll get a fair number of occultations out. Restricting the search to my camera location just gave me 2 hits for the year. But considering it's 2 hits, I don't have to get up in the middle of the night and observe. Again, I think it's worthwhile looking into trying to do this. Now, one of the other things that's actually easier to do in this system than it is with our gear is to find the star. I mentioned earlier that the software already has plate solving code written in it. So I can easily work out what pixel in the image corresponds to the target star. As the camera is not tracking, this pixel will slowly move across the field of view. While I need to double check it, I suspect the short time we need to record an event is just too short for this pixel to move appreciably. Maybe half a pixel, 1 or 2 pixels. So I don't have to worry about tracking the star during the observation. Now, this timing is the most important, and I can think it's also the most difficult part of an occultation system. You just talk to someone like Dave Herold, and he'll tell you all the pitfalls of unreliable timing. Now, the clock needs to be precise, accurate, and reliable. If you consider the power analog video systems that we're probably all familiar with, these produce 25 frames a second. In other words, each frame lasts 1/25 of a second, which is, looking at my calculator, 40 milliseconds. Now, the rule of thumb is that your ruler has to be at least 10 times more accurate than what you're trying to measure. So in this case, we're looking for 4 milliseconds precision and accuracy, and I think we should aim for at least 1 millisecond. So what's the difference between precision and accuracy? Because a lot of laymen get confused what the difference is. Say you wanted to measure the length of the steel rod using this ruler. If you look at the scale there, I hope everyone can see that slide clearly. You can tell it's somewhere between 20 and 21 centimeters long. An analogous situation here would be using a clock that only reads to 1 second. Very coarse, unprecise measurement. With a more precise ruler, you can now measure it as being 20.5 centimeters. This might correspond to a clock that reads to a millisecond. You've got a more accurate, more precise clock. But you could still get an accurate reading using the same ruler if it's just not aligned correctly to the beginning of the rod. In this case, you would think it was actually 23.5 centimeters long. It's not. It's completely inaccurate measurement there. Now, this system could arise in a GPS clock, which hasn't downloaded its almanac yet, of leap seconds. And final example of unreliability is the ruler sometimes isn't even there. This could correspond to a GPS clock that isn't seeing enough satellites. So in effect, it's not operating. So back to measuring the time. The closer you can insert your clock to the camera, the better, in my view, as this reduces the latency between when you actually took the frame and when you put the timestamp on your image. The problem with latency is not only is it often unknown, but sometimes it varies from one frame to the other, depending on where your clock ends up in this trail. So as I say, the ideal is a clock built into the camera. I'm only aware of one camera with GPS-based clock built into it, and that's the very expensive QHY174 GPS. I think it's an M for monochrome. If you know of any others, please let me know at the end of this talk and I'll add it to the list. Now, the camera that's recommended for the GMN system, the Global Meteor Network, is a Sony IMX291 Internet Protocol security camera. So this will probably be the most commonly used camera in the network. So I'll start off by trying to get this to work. Now, I understand it does have a built-in clock, but anecdotally, it's been found to drift a lot. I hope to try and find the specs for the camera and the clock, because if the clock is crystal-based, then there is a possibility of stabilizing it by, for instance, keeping the crystal at a constant temperature and improving the accuracy. Nevertheless, even if it did work, you would still need a GPS system in order to set the time on the clock accurately in the first place. Now, to test if this clock's camera, as it currently is, and also whether temperature control will improve it, I hope to use the sub-in exposure time array, or SEXTA, system, as described by Tony Barry, and Dave Gold, and other authors whose names I can't remember at the moment, in their paper in the Publications of the Astronomical Society of Australia. Now, Tony or Dave G, if you're listening to this, could you please send me a copy of the specs and everything, as the website your paper refers to no longer exists. Now, I'm also trying to work out how I would use Sexta with this particular camera that's in the system, because this camera uses a rolling shutter, and that introduces massive complications. I believe there's a talk later on with someone who's going to be talking about that, so I'll be paying very close attention. So yes, I think that's it. Now, yeah, my notes seem to have disappeared off the bottom of the screen here, so I'm going to have to try and find them. It's weird. I thought presenter mode was perfect, but it's, when you've got lots of notes, they vanish off the bottom. So yes, Sexta. Yes. Yep, I've actually said that. Okay, we'll move on to the next slide. Now, the next best location is between the camera and the computer, in a similar way as done by the IOTA GPS time inserter we're all familiar with. Now, I expect doing that would involve sighting your GPS module between the camera, inside the camera housing, before connecting to the Ethernet port of the camera and providing another connection out to the computer. Now, my first plan is to see if such a system is commercially available, because it's surprising how often you can find GPS systems. If that fails, my second plan is to scream loudly for help, because designing and building one of these modules is well outside of my area of expertise. And the last location is on the camera itself, which in this case is a Raspberry Pi running Linux. Now, the consensus now appears to be that no operating system has a reliable internal clock. However, there is a real-time clock module available for Raspberry Pis. It sits on top of the Raspberry Pi like any other, what they call the module. I can't remember the correct term for it. So it runs independently of the Raspberry Pi. The Raspberry Pi just simply reads the time off it. So you don't have any of the delays that you can have within a computer operating system. So again, I want to use Sexta to see if this clock is reliable enough to use as a time source. I did a quick internet search while I was preparing this talk, just using the search words Raspberry Pi GPS module, and found a dozen cheap commercially available modules already that will plug in. So finding one of these is not a problem. And however, to get the maximum number of cameras in the network measuring occultations, the ideal system would not require any additional hardware to the standard setup, which in this case would be including the Raspberry Pi's real-time clock that comes as standard in the setup. However, I suspect my results from timing this clock will find it's not an acceptable option, and we'll have to go back to using a GPS module somehow. Next stage in the pipeline is recording your results onto tape, as you show here, or moving up timeline a bit onto computer hard drive. Now, while the current global media network software records the frames, it uses a compression algorithm that has been designed by them for recording meteors, and ends up averaging everything that is not a meteor over 10 seconds to produce one FITS file image. In other words, the star images have been integrated over 10 seconds. So that's absolutely hopeless for occultation measurements. So we have to come up with our own recording algorithm, which will run for every frame as it records from the camera, running in parallel to the existing code. Aristo Pavlov has already written a free open source library to record in his Astro digital video format. So that's my first port of call. I'm going to have a look at seeing if I can run that library and record there. Now, I'm still trying to work out whether it's better to record the entire frame in each image or a region of interest centered around the star that's going to be occulted, making that region of interest large enough to include a few comparison stars. I think it will really depend on how big the resulting recording turns out to be. Next step is reducing the data from your video frames to a light curve. In the occultation world, this is a fully manual step done using programs such as LaMovie, Tangra, or PyMovie. If there are any others, I'm not aware of them at the moment. Now, as I mentioned before, most owners of these cameras probably don't even know what an occultation is, let alone have these programs installed and know how to use them. So my thought is, it might even apply to some of us here too, I'm afraid. So my thought is to add code to the system to produce a light curve automatically with a pre-populated report spreadsheet and email it to an occultation volunteer, perhaps one in each region or maybe just one for the entire world, considering there's not going to be a lot of results coming out. Now, this volunteer initially will simply look at the light curve and see whether it's a negative or a positive. If it's a negative, there's not a lot required, and you can probably simply use a pre-populated report and send it off to your regional coordinator, as you usually do. However, if it's a positive, there's a bit more work that needs to be done. And I believe the volunteer would need to have some system that allows them to retrieve the original recording so that they can then reduce it themselves using their favorite tool, PyMovie or Tangra, because doing these reductions sometimes requires a bit of judgment and knowledge, which is impossible to automate, I believe, into a computer program. Now, how I do this, how I get the recording out, is something I'm trying to consider, because they're quite big recordings, to the point where it'd be very problematic to try and email them. So whether I have them available on the Global Meteor Network server, if they approve of that, or whether we set up our own server or even a GitHub repository, because that's a good place to put data, but somewhere where we can easily get at it and analyze it. So if anyone has any suggestions, I'd love to hear them later on. Anyway, once the volunteers got the recording, they need to, as I say, redo the analysis. And one thing I haven't mentioned yet, which will probably be more of a sticking point than anything else, is who gets the credit for the event? Is it the observer who the owner of the camera, or the person who does the reductions? I personally think it should be, the observer should be considered to be the owner of the camera, but the volunteer should also get credit in some manner, perhaps being listed in the second observer field in the report. Also to Dave, Harold and others who want to know who to communicate back to if there are any questions about this event. And again, it probably won't be the owner of the camera. They'll be going, who are you? What's this? Never heard of it. Although, of course. Okay, right. Well. Oh, sorry. I'm nearly at the end.
I didn't realize I was supposed to watch on time as well.
Yeah. Okay. Anyway, I'd also expect the person who does the reductions to keep in close contact with the owner if the owner opts into wanting to do this. So that way we may end up with some more members in the occultation community. Finally, some links here for your information if you want to follow up on any of these things I've talked about. Also, credits of the photos I've stolen, borrowed, whatever you call it, from the internet. So I thought I should credit them. And finally, questions and answers session if I've got any time for those. Oh, stunned mullet look.
Murray, what's the time reference? I've got one. What's the time referencing that GMN themselves need, or is it?
It's not as stringent as occultation requirements. They initially started off just using the Raspberry Pi's clock, and they've recently found that that has been causing some problems, because they do want to have probably sub-second accuracy, but not necessarily millisecond accuracy, to know which frame corresponds to the meteor, where the meteor is on each frame as time goes on. So they are starting to look into it, but I don't think they'll go past using an NTP system.
Okay, Murray, what's actually doing the occultation? I'm assuming it's an asteroid.
Yes, it could be anything that does an occultation, but it won't be doing lunar occultations, as my experience is the camera is so sensitive that even a slither of a moon causes considerable glare around that region of the image. So you can't even see any stars around the moon. So it'll be restricted to minor asteroids. I don't know whether you could do mutual eclipses and events from the Jovian system. I haven't even looked into that yet. I just thought I'd try and get minor planet occultations going first.
There's some stuff remotely, and also a lot of people putting their hands up in the remote team, and I'm not able to jump in. If you could just use the chat window to send any messages, and I'll relay them on to. Tony Barry has sent you the paper.
Thank you, Tony.
And then we have, there's actually quite a bit of discussion going on a side channel regarding using SharpCap, automated observation with SharpCap. So we'll have to try and keep them the chat text or something. But coming down here, let's see, scrolling on. Yeah, Alex from the UK has pointed out that running RMS on a Raspberry Pi with a 291 sensor has a latency of about 2.4 seconds, which isn't really a big problem for the Meteor network because they can just apply a correction, but it's not necessarily great for occultation work. So there's something you have to have a bit of a look into how you're going to calibrate your camera.
The latency, I'm not sure whether it's the camera itself is a 2.4 or it's the total latency to the time where it takes to write to disk. They have been finding some problems where they've been applying the timestamp when the data comes out of the buffer and is about to be written to disk, rather than when the frame first goes into the buffer. But if it's the latency from the camera itself, there is a possibility of it being
There's
fixed.
still more. These remote guys are very busy. Peter's asked, could you go back to the links page again? And I'm sure if he clicks in his Zoom window, he'll be able to follow the links.
I've got about 3 pages of links. So which one?
Yeah, I can't read his mind at this distance. Yeah, I'm assuming it's that one there. But what I could suggest is the PowerPoint should be made available by the website or something, and people can pick up the links and stuff later on.
Yeah, we always do that.
Very hard to do it over Zoom.
We'll have all of the PowerPoints, the PDFs, and be on the website.
Yep. Okay.
At home, sort of thing.
Yep. Eventually, yeah, understood. And Michael Camilleri is happy to talk to you about rolling camera, but you'll probably get a chance to ask Michael questions this afternoon.
Yeah,
he's a talk you were thinking of.
We can do that later on.
All right. Well, lots and lots and lots of questions coming in there. Yeah, but I think we're done for now. Ta.
Okay, I think next on the agenda is Mr. Gold. Are you in a position to talk, though?
Hello.
Hello, coming through.
Good. All right. I'm ready to go. I haven't prepared a PowerPoint per se. I was just going to talk about things. So I just share screen. cannot share screen with some other participant is sharing. So somebody has to unshare the screen. Ah, okay. And I'll try again. Share. Okay.
That's good, Dave.
All right. So this is oh, come on over here. You. So this is about brief events. Is every occultation sacred? Is my title. Hint to my Monty Python. So in the good old days, the minimum